All right, welcome back, everybody. I don't have your exams for you. Sorry. You're gonna have to give me a little more time on that. They take a while, but we'll have them back on Tuesday. We'll go through it and everything. So I'm sure mostly 100% all around. Probably, would you guess? I don't know. I haven't really looked at them yet. Probably, hopefully, we'll see. I could just not grade them and just like give everybody 100%.
You should like that.
Make for a nicer weekend for me. So yeah, probably not gonna do that though. Sorry. Yeah. Well, what we are gonna do today is talk a little bit about the last part of chapter 6. I don't know if we'll make it through the whole thing, but we'll get kind of into it a little bit. So before we do that, are there any questions about previous stuff? I know we just had the exam. I'm glad you're all here. Usually the day after the exam is a little, people decide to stay home, but I'm glad you're here because we are going to do important stuff today. So and please interrupt me if you have questions or you want to talk about anything else. Okay, let's look at, so when we looked at the naming of ionic compounds, we've been working on it the last couple of weeks, and it was on the exam. We were talking about something from the left and something from the right? Something from the metal area, something from the non-metal area. So the rest of chapter 6 focuses on what happens when it's just stuff in the yellow and green together. If there's no metals involved, what's happening there? And those are called covalent compounds because of the way that they interact with each other. So I think we'll just talk about the names first because that's kind of the mode we've been in for the last bit anyway. And then we'll get into why they're called covalent compounds, what that means, and what they actually do with one another. Okay. Oh, this is the wrong file. Okay, let's just start now. So covalent compounds are compounds made of 2 or more nonmetals. And these work a little bit differently, or they're named a little bit differently because we can't make the same kinds of assumptions that we can in ionic compounds. So if you remember ionic compounds, sometimes we automatically know the charge of both just by what they are. Like if it's NaCl, we know Na is going to be +1, we know Cl is going to be -1. No question there. Sometimes we know the charge of 1. So if it's CuCl2, we know chloride is -1, so we can calculate then the copper has to be +2. But we know copper could also have some other charges. So that was the kind of 2 modes. In each way, no matter what category of ionic compounds we were talking about, we always had that sense of like, at least we know something. In covalent compounds, we don't know anything because there's lots of covalent compounds that are made from the same elements. So you can have, if we just look at nitrogen, for instance, you can have N2O, nitrogen and oxygen. You can have NO, you can have NO2, you can have N2O4, N2O5. Those are all known compounds. So none of the ways of naming things that we've talked about really fit here because we can't just call it nitrogen oxide or nitrogen 1 oxide or nitrogen 2 oxide because there's just different numbers of everything. So when we name covalent compounds, we have to specifically say how many of each thing there is. And in some ways that makes it a lot easier because there isn't this like trying to figure out charges and whatever. You just have to say how many there are, and you just have to say it. So the way we say that is with prefixes that you've probably heard before. We'll put a list of them over here. Mono, di, tri, tetra, penta, and hexa. We're not really going to see any compounds that have more than 6 of anything, but that tells you how many of a given compound there are. One, or a given element there are. 1, 2, 3, 4, 5, or 6. So this first compound has 2 nitrogens and 1 oxygen in the formula. So we call it dinitrogen monoxide. Okay, it would be monooxide, but because the two, whenever there's like 2 O's together like that, they just get squished into one. So it's dinitrogen monoxide. What do you think the next one's called then? You want to give it a shot? If that's the rule, what should we say is for the next one?
Mononitrogen monoxide.
Mononitrogen monoxide? Yeah, that would be the name. One little correction, that is the more reasonable way of following the rules. But of course, there's always little shortcuts here, or always little changes here. So we actually drop the mono off the first one, if there is one. And we call this nitrogen monoxide. The only reason for that is if you think about alphabetizing something, if everything that started with mono whatever would all be in the same category, and that's a lot of compounds. So people decided at some point to not do that. If you forget that, think about something that you know, like carbon dioxide is maybe one that you know. And so it's not monocarbon dioxide, it's just carbon dioxide. All right, so using that rule, then what would the next one be?
Dioxide.
Yeah, this one would be nitrogen dioxide. What about this one?
Dinitrogen tetroxide.
Yeah, dinitrogen tetroxide. Again, we drop that A off tetra because it's with another vowel, it's with that O. If that were like fluoride, it would be tetrafluoride. I'm trying to think what other ones start with a vowel. Oxygen. Yeah, but you'd still leave it and call it tetraiodide on that one. I think that's it then, right? So it's just oxygen, but that comes up a lot. Yeah. Okay, and the last one? What would you call this one?
Dinitrogen pentoxide.
Yeah, you got it. Dinitrogen pentoxide. So that's it. That's not too hard, right? The biggest thing that's hard about this is once we learn this way, which is I'm kind of glad we didn't get to it before the first exam, everybody wants to name everything with these rules because these rules are a little bit easier and you don't have to mess with the charges and stuff. So when we, on our next exam, next quiz or something, which will be maybe Tuesday? Thursday? What? Thursday? All right, next Thursday will be the next quiz. That's fine, it'll give us a little more time. So when we do our quiz next Thursday and we have some naming to do, and you see some of the old names come up, like CuCl2, it's going to be tempting to go, oh, that's copper dichloride, because that's an easier way to name things. But we have to go back to the other way of naming it, because that's what separates this from the covalent compounds from the ionic compounds. So if you call CuCl2 copper dichloride, that makes it sound like one of these compounds, and that's going to be confusing to people. So we have to like keep it straight that this only applies when you've got just nonmetals, no metals in your formula. Okay.
For like our second exam, would we have to know, like, are you gonna ask about ionics as well?
Mhm.
So we need to know.
Yeah, all the exams are always cumulative here, so it's like everything. Yeah. Okay, let's try a couple. All right, let's write names for these 4 compounds. See if you can write them down. All right, you got some names? Thinking about it? Okay, what do you got for the first one?
Trichloride.
Close.
Wait, no, phosphate.
Phosphorus trichloride, yeah. Okay, what about SO2? Yeah. Good. CO?
Carbon monoxide.
What about K2O?
Potassium oxide.
Yeah. What? So that one was kind of in there to trick you. K2O is an ionic compound, so it doesn't fit in this category. So we can't call it dipotassium monoxide. We call it potassium oxide because that's an ionic compound. So I use different rules. So like I said, that's the most common mistake with naming these compounds. People usually do a pretty good job of actually naming the covalent compounds. It's picking out which is covalent and which is ionic. And so to pick that out, you're going to look for what? How can you decide? What? A metal, yeah. If there's no metal there, you know, you can use these rules. If there is, you got to go back to the other rules. All right? Okay, so let's talk a little bit more about what these compounds are and what makes it possible for these things to arrange themselves like that. Sorry, I got messed up here. All right, let's take a hydrogen atom. How many valence electrons does a hydrogen atom have? One. How many does it want to have? Two. Because that would be a full bucket, right? So one way that could happen is it could get an electron from some other atom and make a hydride ion. But that's actually not usually how it works, how it gets that extra electron. There's another way that atoms can satisfy their, what we call octet, that like full bucket rule. And the way is called sharing electrons. So we can draw something called a Lewis dot structure, which is just as simple as drawing dots around the atom to show the valence electrons. So hydrogen has one valence electron, gets one dot. And when we see that dot, the usefulness of this kind of a diagram is when we see that dot, we can see that it's missing a pair. We can see that pretty easily that there's like a hole next to it that it would like to get an electron. So what happens with, specifically with hydrogen, is hydrogen can bond to another hydrogen atom where they share both electrons. So when they were normal atoms by themselves, they each had one valence electron. Now that they're together, those two valence electrons count in both atoms. So we say that hydrogen atom has two valence electrons, and also this hydrogen atom has two valence electrons. So those electrons count for both of them. And the way that that works is there's nothing like fancy going on here. It's just that the two atoms are close enough together that where those electrons are, those valence shells, overlap. And so now those electrons are literally within both shells at the same time because the shells are overlapped. And that's where this word covalent comes from. Co means together, so it's the valences together. And the atoms can now share that electron because their valences are together. So now we would say that both of those hydrogen atoms are satisfied. They have their full buckets because they're sharing those electrons and those electrons count in each one. And that's what we call a covalent bond. There's another way that we express a covalent bond in chemistry that you've probably seen before, and that's with a line. So one way to do it is to show those two dots, but another way to do it is to draw a line. And when we draw a line, that line means a specific thing. It means two shared electrons. So that means that it is not appropriate to draw those lines connecting atoms in any other situation except when we're talking about a covalent bond. Does that make sense? We don't draw NaCl and we don't draw a line between the Na and the Cl because that's not a covalent bond. So it doesn't work. That only works when we're talking about covalent compounds. Okay, so let's look at some other ones. What happens when they're bigger molecules or bigger atoms? So how would you draw a Lewis structure for chlorine? How many dots would you put around that atom? 7, right? Because 7 valence electrons. It doesn't really matter how you draw them, but it can be helpful if you pair them up so that you can see those vacancies. So 1, 2, 3, 4, 5, 6, 7. And we can see that there's one there without a pair. We can quickly visually see that there are 7 dots there and not 8. So chlorine wants 8 for a full shell, right? Because that's number 3. So in order for that to happen, it could gain an electron, which is the chloride ions we've been talking about. But it could also make a covalent bond with another atom. And it can make a covalent bond with itself, with chlorine, or with hydrogen, or with whatever, some other stuff. So we could draw 2 chlorine atoms helping each other out, sharing electrons to make this kind of a compound. So then when it has that covalent bond in place, we can now recount this. And we can say, well, this chlorine has all its 8 electrons. It has a full octet. And this chlorine has its 8 electrons. It also has a full octet because those shared electrons now count in both valences. Does that sound okay so far? Can you see how that works? So when we draw a structure, a Lewis structure for chlorine, a way that we can draw it is to show a line connecting those two. And then sometimes we also write those leftover electrons on there as well that don't bond, to really get a full picture of what the electrons are doing. But that line in the middle specifically means just two shared electrons. That's what that's talking about. All right. Okay, let's look at how that works for some other compounds. What if you have oxygen? How many valence electrons does oxygen have? 6. So we got to draw 6 electrons on oxygen. 1, 2, 3, 4, and I'm going to distribute those last 2 like this. Doesn't matter, you could draw them together, that's fine. And what about, so how many does it want? 2 more, right, to get 8 total? So that means we can think of like a space here and a space here where it would like to get 2 more electrons. So one way that it could do that would be, let's say, binding with hydrogen. So it could make 2 bonds with 2 hydrogen atoms and then end up with something like this. And now all of those elements have their valences satisfied. Oxygen has 8, and each hydrogen has 2, which is what they want also. So you've got hydrogen with 2, and then oxygen with 8. And this molecule is water, right? So we might also write it, oops. So we might also write it like this. Right, that's of course H2O, water. What if oxygen wants to bind with itself the way that chlorine or hydrogen does? Could that work? Let's try it. If we share 2 electrons like this, we've got something like that. So are those oxygens satisfied now? Not quite, right? We can say they each have 7, but not 8. So what should we do?
Double bond.
Yeah, you can actually share 2 pairs of electrons. So along with those that are already shared, we could share these 2 as well. And we could just kind of put those all in the middle and say that these oxygens share 2 pairs of electrons. And so now this one, we would count all those shared ones. Okay, that has 8 electrons. This one also 8 electrons. Right, so we're good. And we'll get into this more structure stuff, more of the structure stuff in a later chapter. But just to get an idea of what these covalent bonds are and what that means, we would draw this like this. And that would be called, however you express it, a double bond, meaning 2 pairs of shared electrons. You can also have a triple bond, which is 3 pairs of shared electrons. Okay, so one thing that comes out of this is that on their own, some elements always exist as a double, like this. Because of their valence electrons, they always want to associate with another one so that they can hang around with a full octet of electrons, a full shell of electrons. These are known as the diatomic elements. So elements that exist as 2 atoms together. And they are hydrogen, nitrogen, oxygen, and then the whole halogen category. So I read it in that order because that's kind of how it goes on the periodic table. If you want to just memorize a shape or something, that helps me remember which ones are which. But it's important to know which ones of these are together as a dimer, because when we get into the next chapter, we're going to talk about chemical equations. And so if you want to know that something reacts with oxygen, you need to know that that means you have to write down O2, not just O. Or if it's something reacts with bromine, that it's Br2 and not just Br. Or hydrogen is H2 and not just H, because it will change, it'll mess up the whole equation if you just write the letter instead of understanding that it's together. And hopefully now you can also understand why those have to be that way. And it's because of the valence electrons and what they have to do to be stable. So you get that so far? You good? Okay. So then I want to pull this picture out of the book. Because it's not going to look as nice if I draw it. But we talk about covalent bond as this like sharing of electrons. But in many cases, in most cases, it's actually not an even sharing. It's an uneven sharing. It's an unequal sharing. And let's look at what that means once we get there. Maybe? No? We're not gonna get table contents here? Come on, internet, you can do it. All right, well, I will draw it if I can't get a nice picture. Okay, while that loads, let's just draw it. So this goes under the category of something called polar covalent bonds. So let's imagine something like hydrogen and chlorine together. Hydrogen has 1 valence electron. Chlorine has 7. You look there? It's become unresponsive. Okay. Yeah, sure has. So the way that those are going to go together, the same thing we've just been talking about, they're going to share 2 electrons so that hydrogen can have a full shell and chlorine can have a full shell also. And they're going to make this kind of a compound. Like that. So now we've got our covalent bond in the middle. We've got chlorine with 8 electrons and then hydrogen with 2 electrons. Everything looks good. So the issue with this is that there's not even sharing here. In other words, those 2 electrons that are shared are not evenly shared equally between both atoms. Any idea where they're going to spend more time? Chlorine, yeah. So if we were to draw like a comparison here, hydrogen's covalent bond versus chlorine's covalent bond. Hydrogen's covalent bond, kind of the electrons hang around both hydrogens equally. HCl's covalent bond looks more like this. So the electrons spend much more time around chlorine. Chlorine pulls the electrons toward it. And that makes for an uneven sharing of electrons. And the consequence of that is an actual charged, almost ionic type situation. Because electrons have a charge, right? What's the charge of an electron? -1, yeah. So if the electron spends more time on one side, what's the charge of that side going to be? More negative, and the other side's going to be more positive. And that's exactly what happens. So, did we load up yet? Oh, we did, okay. Let's see if we can find a nice picture of these things. There's one, but it's not great. Yeah, here we go. We'll talk about these numbers in a minute, but let's just pull this up. So take a look at those pictures down there. And you see this is like our hydrogen situation. We had 2 hydrogens shared together. We'd have this equal sharing. If we had H and Cl, we have this unequal sharing. And because the Cl side gets the electrons, there's now a partial negative charge around that chlorine. This is a Greek letter, delta. And so if we say something like delta minus, what we're saying is there's a partial negative charge on that side. So we don't have a full charge. It's not like an ion. That's what we have next to it over here. It's not like one's completely negative and one's completely positive, but one's like a little bit negative and one's a little bit positive. And that's what happens if we have these polar covalent bonds. So how do we decide, or how do we figure out if we have a polar bond or not? We look at something called electronegativity. And you see that word in the table there, and we're going to take a look at what that means. Electronegativity is the ability of an atom to attract, let's not just say electrons, let's say to attract shared electrons. So we're not talking about an ion situation where the thing is like pulling electrons from other places. We're just talking about if you already have a covalent bond, an atom with a high electronegativity can attract those electrons in the covalent bond toward itself. And so we have to look that value up on a table. It's measured by experiment. The table looks like this. Okay, so there you see the electronegativities for many of the elements. Now, metals in general have very low electronegativities. So we don't even really worry about those so much because they're so low. Non-metals have variable electronegativities. And the important things to remember are these arrows. So in many cases, we can decide if a bond is going to be polar or nonpolar just by remembering the trends. So the most electronegative element on the table, anybody see it? Fluorine, right. And the least? Yeah, cesium. So you can imagine a big trend going from the bottom left corner to the top right corner up to fluorine. Everything kind of trends toward fluorine. So even if you don't know these numbers, you could say, well, a CF bond is probably going to be polar because we know F is more electronegative than C because it's more to the right. All right, because we won't always have these numbers, we should still be able to guess. Now, some of them we won't. Some of them will be too hard to guess without actually looking up the numbers. But like if they're really close or if they're going the opposite direction, but if we need to, we can look up the numbers. So, so let's look at a couple different bonds. Okay, and decide if these things are polar or not. So when we decide if a bond is polar, we're going to use this kind of rule of thumb, which is, again, it's a trend. It's like a continuum. It's not like a set number. But at some point, people decided anything greater than 0.4 of a difference in electronegativity, we're going to call that polar. And anything less, we're going to say is nonpolar. So if we take this first one, SBr, we look, S is 2.5, Br is 2.8. So what's the difference in electronegativity there? 0.3. So we're going to say that's too low. And this is a nonpolar bond. That means that that particular type of covalent bond in a compound, the electrons are not going to be attracted to one side versus the other. They're going to be as roughly equally shared. What about HCl? What's the difference in electronegativity there? 0.9, right? You see that? H is 2.1, Cl is 3.0. So that's 0.9. We'll say the difference here was, what was it, 0.3? The difference is 0.9. So that one we call polar. CH. What's the difference there? Yeah, 0.4. So what would we call that? That one is nonpolar. It's like right on the, yeah. So it has to be greater than 0.4 for us to call it polar. What about CO? Yeah. So we call that polar. All right, so you see how that works? Okay. The last thing then is talking about why that's important. So we're going to skip, based on the syllabus and the objectives, we're skipping section 6.7, which talks about how to determine the shapes of molecules. So you're not going to have to do that. However, you don't need to know all these different shapes for these different groups. However, we do want to be able to use those shapes to predict polarity. And this is how that works. We talked now about polar versus nonpolar bonds. Now let's talk about just break this thing. Guess not. So a molecule is a covalent compound that's made up of some atoms and that like ends at a particular point. And to determine if a whole molecule is polar or nonpolar, you have to add up the polar bonds. So if it only is made up of nonpolar bonds, like it's only made of C and H and there's CH bonds and we know that's nonpolar, then we know it's nonpolar and we don't have to do anything. But if it has polar bonds, we need to add up those polar bonds and decide if it's overall polar or not. So let's use water as an example. Does anybody know what the shape of a water molecule is? Just from your previous, whatever. So what?
Like an upside down V.
Like an upside down V, yeah, or a V. If doesn't matter which way you write it, but yeah, we'll go with the upside down V. So here's water. You've got an O, an H, and an H, and it kind of makes this V shape. And again, we're not going to do the sections where we figure out what molecule shapes are. We're just going to say, I'm just going to tell you the shapes of stuff. Okay, so the first question we need to ask is, are the individual bonds polar? So in this water molecule, what are the individual bonds made of? O and H, they're OH bonds. So does OH make a polar bond? Yes, it does. Do you see that? Big difference in electronegativity. So that means the electrons are going to be pulled toward the oxygen. Yep.
When it comes to quizzes and exams, will you give us that chart of their polar
Yes.
numbers? Okay. I didn't know if we had to like memorize.
You don't have to memorize the numbers. You should know the overall trend.
Okay.
And sometimes you can figure out the answer from the overall trend, but sometimes you can't. So I would give you the numbers if you need them. Okay, so the individual bonds are polar. Yes. You have OH bonds that are polar. The electrons are pulled toward the oxygen. So that means we get a little bit negative on the oxygen and a little bit positive over on the hydrogen. Okay. We can express that as a vector, which is just saying a value that also has a direction. And it's usually drawn like this, a little plus sign that gets extended to an arrow showing where the electrons are going to. So in this case, the electrons go toward the oxygen. So we can draw a little arrow that says the electrons go toward the oxygen because that's the one that's more electronegative. Let's do that on the actual molecule as well. So for this bond, we've got a partial negative here, partial positive here. And that means we have an overall, what's called a dipole moment that goes that direction. An overall vector, meaning the electrons are getting pulled toward that oxygen in that particular bond. Then we do the same thing for the other one. And now how do we add those two together? Anybody remember how to add vectors? No? Okay, that's fine. Well, you line them up head to tail, almost like you're taking a path, and you figure out where it goes. So we would say, okay, the first vector goes like this way. And then the second vector is the same size going this way. So then our overall sum of those vectors starts here and goes to here. And that sum is known as the overall dipole moment. And it's the answer to the question, is this molecule polar? So is the whole molecule polar? And the answer is yes for water. That means if you had something like an electric field, water molecules would line up in that way. And the last part of the chapter, when we talk about intermolecular forces, this is what we're going to go back to. We're going to refer to this. So it tells us that a water molecule, another way of thinking about it, you don't like adding up the vectors and stuff, which is fine. You can also think about where are the positive charges and where are the negative charges. In water, the positive charges are all around the, well here, we know it's partial. Let's just draw a bunch of little pluses. We know in water that the positive charges are all around the hydrogen. Again, they're not full charges. It's just like area of positiveness. And the negative things are all around the oxygen. And we could imagine that we can draw a line right through the middle of that oxygen molecule or that water molecule. And everything on top of that line is negative, and everything on the bottom of that line is positive. And that's what we mean by polar. That word polar means separated into a negative side and a positive side. So if you can draw a molecule and you can draw all the positive charges on one side and all the negative charges on another side based on the polarities and the electronegativities, then you know you have a polar situation, a polar molecule. So let's try that with some different shapes of molecules and see how that works out. Let's look, for instance, at BF3. So BF3 is a flat molecule, and all of the bonds kind of go to the corners of a triangle. So they're all evenly spaced, going to the corners of a triangle. Do you think the individual BF bonds are polar? What do you think? Yeah? Why?
Because fluorine has a really high electronegativity charge.
Yeah, pretty much anything with fluorine is going to be polar, right? And if we look at the periodic table, boron is several spots away from fluorine. So we would expect that probably is going to be pretty polar. And if we go back to look at the actual numbers, we see, oh yeah, it is quite polar. BF2 to 4 is a big, big difference. All right, so that's going to be quite polar. So we've answered that first question. Are the individual bonds polar? Yes. So let's draw them on the structure. Where would the negative go and where would the positive go?
Negative is on the fluorine.
Yeah, negative's going to the more electronegative one, which is fluorine. And that makes the positive, oops, on boron. Okay, so now we've got our polar bonds there, and we can also draw in those vectors that we talked about. Showing the electrons being pulled toward fluorine in 3 different directions. So do you think when we add those up that there will be an overall polarity to this molecule or not? Do you see a polar side or a positive side and a negative side? Or is it kind of symmetrically distributed? What do you think?
I mean, if you draw the line that way, it would be distributed.
Right. Yeah.
It's right in the middle.
So exactly. So that tells us that we probably are not going to get a polar situation here. And if we actually add those vectors up, what you get is like this one, and then this one, and then this one. And so you end up back where you started, which means you have a 0 overall dipole moment. So those vectors all cancel each other out. And this molecule is nonpolar overall. Even though it has very polar bonds, the molecule itself is nonpolar. And the other way to look for that, if you don't feel good about the vector drawing adding thing, which is fine, is like what Lauren said, that if you try to draw a line and cut this molecule in a particular way, you can't say, here's a negative side and here's a positive side. No matter how you, like if I go like this, I still have two negatives on the outsides. If I go like this, I've got negatives on top and negative on the bottom. So no matter how I try to cut it, I'm always distributing my negative charges around, and that makes for a nonpolar overall molecule that's made up of polar bonds. So let's look at another example like that. We'll look at PCl3. That's going to be a phosphorus with 3 chlorines. And the way that it is distributed, I'm going to try to draw this as best I can. We're going to use this notation where the thick line means it's coming out at you, and the dashed line means it's going back. So that can be a little bit hard to see. Let me pull up another program that will help us look at that. Let's see if I can get the thing to go in the right way. Guess not. Let's see, maybe I can.
Like a three-sided pyramid, right?
Yeah, it's kind of like, yeah, like a three-sided pyramid. I don't know how I can make this one do it. Whoop. Whoop, come on, just. What's it doing? Is this inappropriate for class? Is it going to just keep doing that? Oh, calculation and progress. It's trying to calculate like where the lowest energy is, what the best arrangement is for it, and it should figure out that it needs to be in that bed spot, but it's just kind of doing that. So I don't know. All right, we'll just let it do that for a while and see what happens. Okay, so anyway, you get the idea that it's like on the corners of a triangle pyramid type thing. So if we go back up and look at the PCl3, are those polar bonds or not?
Yes.
They are. Do you see the difference in electronegativity between P and Cl is about 0.9? Yeah. So that tells us that there is a difference here, and we can put partial positive charges on the phosphorus and partial negative on the chlorine. So do you see polarity in that molecule or no?
Yeah.
How? Yeah.
You can draw a line.
Yeah, you can draw the line and you can say, oh, everything on the bottom is negative and everything on the top is positive. If we want to be fancy, let me move this over so we have a little more room. It's actually kind of like a plane, since we're sort of drawing in 3 dimensions here. But if you imagine we could like kind of cut this like that, underneath that phosphorus, everything on top of that plane is positive, everything below it is negative. So this thing makes this shape that's like kind of like this, with the P at the top and the Cl's down here. And if we cut like through the middle there, everything on top is positive and everything on the bottom is negative. So that's another polar type situation. So that molecule is polar and has an overall dipole moment. Let's see how our calculation's going. Oh, good. So I figured it out. All right. After all of that action, it came up with that this was the best structure, which is true. So you have this kind of a thing, and you can see now that you can imagine cutting right through the middle here. All the positive stuff from the phosphorus is on top, and the negative stuff from the chlorine is on the bottom. All right. In fact, just so we have that, if anybody needs it, let's copy this picture over to the notes. We've got it. Yeah. Okay, so that's the shape of that one. Now, if I ask these kinds of questions, I would always give you the shape and then ask you to come up with whether or not it's actually polar. So here's another example. I'm going to give you two compounds to look at. One of them is called carbon tetrachloride, CCl4, and the other one is called dichloromethane, CCl2H2 or CH2Cl2. And I'm going to use this thing because I know this one's going to work. I shouldn't have said that. I think this is going to work. All right, so where did I go here? So I don't even have to do silly games with. So there's our CCl2H2, and you see a really kind of unusual structure here. Let me add those other two. Those other two chlorines so we can see it more evenly before we start messing with it. Okay, so this structure is called a tetrahedral structure. And it's essentially that same structure that we just saw with the PCl5, except now we also have a fourth one coming out of the top. You see that? There's kind of two that are in the same plane like this, almost like water, and then one that comes out at you and one that goes back. Can we see that? So there's CCl4. And the way we draw that on paper, since we can't really express all those dimensions unless you're good at drawing stuff, which that's great, but I'm not, is we draw the two that are in the plane, and then we draw the one going back and one coming out at you with what's called a dash and a wedge. So there's our wedge, and there's our dash. And those are actually right on top of each other in the physical structure. We just draw them a little bit apart so we can see them. Let me make this a little bit smaller, and we'll import it into our document so we can see it right next to there. CCl2H2 has the same geometry, same tetrahedral geometry it's called. Called that because that shape that we drew before, that like triangle pyramid, is called a tetrahedron. So that carbon would be right in the middle. And then the two H's are on this other side here. Okay. So think about the bond vectors in those two scenarios and decide whether those molecules are polar or not. Just to help you, a CCl bond, we'll go back down a second. A CCl bond is polar, just barely. A CH bond is not. So what do you think? Are those molecules overall polar or not? Let's all think about it. And
Can you split the ClH2 like that way to make it polar? Because like the CH bond is not polar, but the
Right.
Cl bond is polar.
yeah,
So can you split it to make part of it polar?
right. Yep.
Okay.
Yep. So then what would you say for the overall molecule?
That it's polar.
Yeah, it is. So you, if you look at this one, the CLs are going to be minus and the C is plus. And then we've got nothing really between the C and the H. So we can imagine a line right here that separates the positives from the negatives. I mean, I drew those in a bad spot, but let's see if I can fix that. Right, so if you cut in between those C and Cl bonds, you've got a positive side and a negative side. And so that is overall polar. So that molecule is polar. What about the other one? Shaking your head. Not polar, or you don't know?
I don't think.
You don't think it's polar?
No.
Anybody else? Agree? Not polar? Disagree? What do you think?
No.
Not. Yeah, you're right. It's not. Same reason. We can make the chlorines negative and the carbons positive for each bond, because those are polar bonds. But in this case, the positives are all kind of surrounded by the negatives that are symmetrically oriented around the structure. And it's hard to imagine adding those vectors in 3 dimensions, but if you could, you actually would cancel them both out, because the two of them, so let me show you here. These two vectors would add up to being straight out this way, and then these two would add up to being straight out this way, and the two straight out this ways would cancel each other out. And so the overall adding of those vectors would be 0. But the other way to look at that, that's probably a little bit easier, is just to see that there's no way you can draw a line in the structure and have the positives be on one side and the negatives be on the other side. And in general, any highly symmetric structure like this, where you have a central atom and then a bunch of atoms evenly distributed around the outside, whether it's in 2 dimensions in a triangle or 3 dimensions in a tetrahedron, you're going to have a non-polar molecule, because there just isn't a positive side and a negative side. It's all kind of symmetrically distributed. And so that's how you decide if it's polar or not. So then on Tuesday, we're going to go into what is the consequence of this, and how can we use the polarity of molecules to decide things like boiling point and water solubility and some other issues. Sound good? And we'll talk about the exams too. All right, have a good weekend.
Hello.